let me go into the bigger picture of learning, because what I talked about so far is one type of learning. Happens to be by far the most popular and the most used. But there are other types of learning. Okay, so let's talk about the premise of learning from which the different types came about. That's what learning is about. Okay. This is the common premise that is common between any problem that you would consider learning. You use a set of observations, what we call data, to uncover an underlying process. In our case, the target function. Now, you can see that this is a very broad premise. And therefore, you can see that people have rediscovered that over and over and over in so many disciplines. Okay, can you think of a discipline other than machine learning that uses that as its exclusive premise? Anybody have taken courses in statistics? Okay, so in statistics, that's what they do. The underlying process is a probability distribution. And the observations are samples generated by that distribution. And you want to take the samples and predict what the probability distribution is. And over, there are so many disciplines under different names. Now, when we talk about different types of learning, it's not like we sit down and look at the word and say, okay, this looks different from this because the assumptions look different. What you do is you take this premise and applying it in a context. And that calls for a certain amount of mathematics and algorithms. If a particular set of assumptions takes you sufficiently far from the mathematics and the algorithm you used in the other disciplines, that you sort of, it takes on a life of its own, and it develops its own math and algorithms, then you declare it a different type. Okay? So when I list the types, it's not completely obvious, just by the slide itself, that these should be the types that you have. But for what it's worth, these are the most important types. First one is supervised learning. That's what we have been talking about, and I will discuss it in detail and tell you why it's called supervised. And it is by far the concentration of this course. There is another one which is called unsupervised learning. And unsupervised learning is very intriguing. I will mention it briefly here, and then we will talk about a very famous algorithm for unsupervised learning later in the course. And the final type is reinforcement learning, which is even more intriguing, and I will discuss it in the sort of a brief introduction in a moment. Okay, so let's take them one by one. Supervised learning. So what is supervised learning? Okay. Anytime you have the data that is given to you with the output explicitly given, here is the user and movie, and here is the rating. Okay? Here is the previous customer, and here is their credit behavior. It's as if a supervisor is helping you out in order to be able to classify the future ones. That's why it's called supervised. So let's take an example of coin recognition just to be able to contrast it with unsupervised learning in a moment. Okay, so let's say you have a vending machine, and you would like to make the system able to recognize the coins. So what do? You have physical measurements of the coin. Let's be simplistic and say we measure the size and mass of the coin you put. Now, the coins will be quarters, nickels, pennies, and dimes, 25, 5, 1, and 10. Okay? And when you put the data in this diagram, they will belong to, so the quarters, for example, are bigger. Okay, so they will belong here. And the dimes in the US currency happen to be the smallest of them, so they are smallest here. And there will be a scatter because of the error in measurement, because of the exposure to the elements or whatnot. So let's say that this is your training data, and it's supervised because the things are colored. I gave you those and told you they are 25 cents, 5 cents, etc. So you use those in order to train a system, and the system will then be able to classify a future one. Okay? So, for example, if we stick to the linear approach, you may be able to find separator lines like those. And those separator lines will separate based on the data, the 10 from the 1, from the 5 from the 25. And once you have those, the data, you can bid farewell to the data. You don't need it anymore. And when you get a future coin that is now unlabeled, you don't know what it is, that the vending machine is actually working, then the coin will lie in one region or another, and you're going to classify accordingly. So that is supervised learning. Now let's look at unsupervised learning. For unsupervised learning, instead of having the examples, the training data, having this form, which is the input plus the correct target, the correct output, okay, the customer and how they behaved in reality in credit, okay? We are going to have examples that have less information, so much less, laughable. I am just going to tell you what the input is. And I'm not going to tell you what the target function is at all. I'm not going to tell you anything about the target function. I'm going just to tell you, here is the data of a customer. Good luck. Try to predict the credit. Okay. Well, how in the world are we going to do that? Okay. Let me show you that the situation is not totally hopeless. That's what I'm going to achieve. I'm not going to tell you how to do it completely. But let me show you that the situation like that is not totally hopeless. Okay. Let's go for the coin example. Okay? So for the coin example, we have data that looks like this. If I didn't tell you what the denominations are, the data would look like this. Right? You have the measurements, but you don't know, is it a quarter? You don't know. Now, honestly, if you look at this thing, you say, okay, I can know something from this figure. Things tend to. So I may be able to classify those clusters into categories without knowing what the categories are. That would be quite an achievement already. You still don't know whether it's the 25 cents or whatever. But the data actually made you able to do something that is a significant step. You are going to be able to come up with these boundaries, okay? And now you are so close to finding the full system. So unlabeled data actually can be pretty useful. Now, obviously, I have seen the colored ones, so I actually chose the boundaries right because I still remember them visually. But if you look at the clusters and you have never heard about that, especially these guys might not look like two clusters. They may look like one cluster. So it actually could be that, okay, this is ambiguous. And indeed, in unsupervised learning, the number of clusters is ambiguous at times. Okay? Okay. And then what you do, this is the output of your system. Now I can categorize the pennies into types. Okay? I'm just going to call them types. Type 1, type 2, type 3, type 4. I have no idea which belongs to which. But obviously, if someone comes with a single example of a quarter, a dime, etc., then you are ready to go. Okay? Whereas before, you had to have lots of examples in order to choose where exactly to put the boundary. Okay? And this is why a set like that, which looks like complete jungle, is actually useful. Let me give you another interesting example of unsupervised learning, where I give you the input without the output, and you are actually in a better situation to learn. Let's say that your company, or your school in this case, is sending you for a semester in Rio de Janeiro. Okay? So you're very excited, and you decide that you'd better learn some Portuguese in order to be able to speak the language when you arrive. Okay? Not to worry, when you arrive, there will be a tutor who teaches you Portuguese. But you have a month to go, and you want to help yourself as much as possible. You look around, and you find that the only resource you have is a radio station in Portuguese in your car. Okay? So what you do, you just turn it on whenever you drive. And for an entire month, you are bombarded with Portuguese. Tudo bem, como vai, valeu, stuff like that comes back. After a while, without knowing anything, it's unsupervised, nobody told you the meaning of any word, you start to develop a model of the language in your mind. You know what the idioms are, etc. You are very eager to know what actually tudo bem, what does that mean? You are ready to learn, and once you learn it, it's actually fixed in your mind. Then when you go there, you will learn the language faster than if you didn't go through this experience. So you can think of unsupervised learning in one way or another as a way of getting a higher level representation of the input. Whether it's extremely high level as in clusters, you forgot all the attributes and you just tell me a label, or higher level as in this, a better representation than just the crude input into some model in your mind. Okay? Okay, now let's talk about reinforcement learning. In this case, it's not as bad as unsupervised learning. So again, the benefit of supervised learning, you don't get the correct output. What you do is, I will give you the input. Okay, thank you very much. That's very kind. What else? I'm going to give you some output. So some output, the correct output? No, some output. Okay, that's very nice, but doesn't seem very helpful. It looks right now like unsupervised learning, because in unsupervised learning, I could give you some output. Here is a dime. Oh, it's a quarter. It's some output, okay? So the information next one. I'm going to grade this output. So that is the information provided to you. So I'm not explicitly giving you the output, but when you choose an output, I'm going to tell you how well you are doing. Reinforcement learning is interesting because it is mostly our own experience in learning. Think of a toddler and a hot cup of tea in front of her. She's looking at it and she's very curious. So she reaches to touch and she starts crying. The reward is very negative for trying. Now, next time she looks at it and she remembers the previous experience and she doesn't touch it. But there is a certain level of pain because there is an unfulfilled curiosity, okay? And the curiosity kills the cat. In 3 or 4 trials, the toddler tries again. Maybe now it's okay. And then, okay. Eventually, from just the grade of the behavior of to touch it or not to touch it, the toddler will learn not to touch cups of tea that have smoke coming out of them, okay? So that is a case of reinforcement learning. The most important application, or one of the most important applications of reinforcement learning, is in playing games, okay? So backgammon is one of the games, and think that you want a system to learn it. So what you want to take the current state of the board, and you roll the dice, and then you decide what is the optimal move in order to stand the best chance to win. That's the game. So the target function is the best move given a state. Now, if I have to generate those things in order for the system to learn, then I must be a pretty good backgammon player already. So now it's a vicious cycle, okay? So now reinforcement learning comes in handy. What you are going to do, you are going to have the computer choose any output, a crazy move for all you care. And then see what happens eventually. So this computer is playing against another computer. Both of them want to learn. And you make a move, and eventually you win or lose. So you propagate back the credit because of winning or losing, according to a very specific and sophisticated formula, into all the moves that happened. Okay? Now you think like completely hopeless because maybe this is not the move that resulted in this, it's another move. But always remember that you are going to do this 100 billion times. Not you, the poor computer. You are sitting down, sipping your tea, okay? The computer is doing this, playing against an imaginary component, and they keep playing and playing and playing, and in 3 hours of CPU time, you go back to the computer, maybe not 3 hours, maybe 3 days of CPU time, you go back to the computer, and you have a backgammon champion. Actually, that's true. The word champion at some point was a neural network that learned the way I described. Okay? So it is actually a very attractive approach because, okay, so machine learning now, we have a target function that we cannot model. That covers a lot of territory. I've seen a lot of those. We have data coming from the target function. Okay, I usually have that. And now we have lazy man's approach to life. We are going to sit down and let the computer do all the work and produce the system we want. Instead of studying the thing mathematically and writing code and debugging, I hate debugging, okay? And then you go, no, we're not going to do that. The learning algorithm just works and produces something good, okay? And we get the check. So this is a pretty good deal. It actually is so good, it might be too good to be true. Okay, so let's actually examine if all of this was a fantasy. So now I'm going to give you a learning puzzle, okay? Humans are very good learners, right? Okay? So I am now going to give you a learning problem in the form that I described, a supervised learning problem. And that supervised learning problem will give you training set, some points mapped to +1, some points mapped to -1, and then I'm going to give you a test point that is unlabeled. Your task is to look at the examples, learn the target function, apply it to the test point, and then decide what the value of the function is. After that, I'm going to ask who decided that the function is +1 and who decided that the function is -1. Okay? It's clear what the deal is. Okay? And I would like our online audience to do the same thing. And please text what the solution is, just +1 or -1. Okay? Fair enough? Let's start the game. Okay? What is above the line are the training examples. I put the input as a 3x3 pattern in order to be visually easy to understand. But this is just really 9 bits worth of information. And they are ones and zeros, black and white. And for this input, and this input, the value of the target function is -1. For this input, and this input, the value of the target function is +1. Now, this is your data set. This is your training set. Now you should learn the function. And when you are done, could you please tell me what your function will return on this test point? Is it +1 or -1? I will give everybody 30 seconds before I ask for answers. Maybe we should have some background music. We should, okay. Okay. Okay, time is up. The learning algorithm has converged, I hope. And now we apply it here, and I ask people here, who says it's +1? Okay, thank you. Who says it's -1? Thank you. I see that the online audience also contributed.
Yeah, so the big majority says +1.
But are there -1s?
2 -1s.
Okay, cool. Okay. I don't care if it's a +1 or -1. What I care about is that I get both answers. Okay, that is the essence of it. Why do I care? Because in reality, this is an impossible task. I told you the target function is unknown. It could be anything, really, anything. And now I give you the value of the target function at 6 points. Well, there are many functions that fit those 6 points and behave differently outside. For example, if you take the function to be +1 if the top left square is white, then this should be -1, right? If you take the function to be +1 if the pattern is symmetric, okay? So you can see it. So let's see. If I said it the other way around. So the top one is black, it would be -1. So this would be -1. If it's symmetric, it would be +1. So this would be +1 because this guy has both this black and also is symmetric, right? And you can find infinite variety like that. And that problem is not restricted to this case, okay? The question here is obvious. Function is unknown. You really mean unknown, right? Yes, I mean it. Unknown, anything. Yes, I do. Okay? You give me a finite sample. Well, it can be anything outside. How in the world am I going to tell what the learning outside is? Okay, that sounds about right. But we are in trouble because that's the premise of learning. If the goal was to memorize the examples I gave you, that would be memorizing, not learning. Learning is to figure out a pattern that applies outside. And now we realize that outside, I cannot say anything. Okay, does this mean that learning is doomed? Well, this is going to be a very short course, okay? Well, the good news is that learning is alive and well. And we are going to show that without compromising our basic premise. The target function will continue to be unknown. And we still mean unknown. And we will be able to learn. And that will be the subject of the next lecture.